Just depends upon what you guys went over. So, when you have a model of an atom, what you've learned in the past, it has borders. It has places where things are located. Alright? So this is a model of an atom, and it doesn't really justify an atom. It's just a way that you can visually see where things are located. Okay? So, you're going to, if you want to draw this, you can. So you got a visual off to the side. I know you don't have a lot of room, but if you want to, you can. So, a proton is within the atom. So last chapter, a unit, we said, hey, matter can be in these four areas. It could be an element, compound, or mixture. Homogeneous mixture, or heterogeneous. This is how you can kind of draw them if you want to. Okay? This would be an example of a compound. This would be an example of an element. This is an example of a molecule. Okay? We also looked at properties and changes that some of you struggled with. If you guys had that sheet that you guys used for the lab, it said these words represent physical changes like boiling, melting, freezing. These represent chemical, which is like burning, combustion, those type of things, corroding. So that's all that section was about. Now we're getting into the periodic table, and we're looking at a part of the periodic table that talks about atoms. An atom is the smallest particle of an element that has the same properties of that element. If you break an atom apart, you no longer have the properties of that element. You don't have that element anymore. Well, the only way that an atom can be broken apart is nuclear fusion. Okay? We can get that later. Okay? Okay? So, the only way it can be broken apart is a process of separating it out. And that takes something beyond what you can do in a normal lab. So, subatomic particle, proton, what charge is it?
Electron.
No, what charge is it? So, there's two charges. So, what charge is a proton? Positive. This is an easy way to remember. P-R-O-T. See that T? Positive.
Plus.
Looks like a positive. Okay? So proton's positive. Where is it located? In the atom. So if this is my atom, where in that area is a proton going to be?
Center, isn't it?
Center. It's right here. This is where the proton's at. Okay? So how do they know that? How do they know protons? I mean, they can't even see an atom.
In a nucleus, isn't it?
Okay, yeah. They can't even see an atom, so they do it by a process of taking a bunch of atoms like that's in here. This is about this is over 10,000 atoms thick. You guys see that? You guys see those 10,000 atoms? Okay. So how do I know that?
Yeah, how do you know that?
Because they did later on, they go through a process, and I actually do this in AP Chemistry. They have to tell me how many atoms of a thick that's in like a galvanized zinc. So they take the layer off, and they know some more information about zinc, and they can tell me how thick the layer is in atoms. Okay? So what they did, this one scientist, Rutherford, it's called the Rutherford's gold foil experiment. He sent these positive charged particles through there. Okay, he had something radioactive and was encased in a lead box, and it had a little hole, and it bounced around in there, that particle, until it shot out like a gun, and it went through the gold foil. Guess what? 999 out of 1,000 on average went straight through. Okay? Now you think 10,000 atoms thick, it's not even coming in close contact with anything. Well, there's one that out of that 999 that deflected. And it went a different direction. And they had a screen, a fluorescent screen around it that detected this particle. And most of them hit directly behind but there would be one that would deflect off to the side. So what was that one? Now, that particle is positively charged.
So it's a
That's
positive
going
one.
through. So what do you think that particle is coming in close proximity to cause it to be deflected?
Same charge.
The same charge, right? Because opposites attract, like charges repel. Guess what? It was coming close to this area. So they go, okay, it's positive. There must be something in there that's positive that's deflecting it. It's the nucleus. They come up. But if 999 out of 1,000 are going through there, how big is the nucleus?
Very small.
Super duper small. Okay, so like Memorial Stadium, if you go there and Tom Osborne Field, you put on the 50-yard line a penny, the electron cloud, we say, would be like the upper part of the stadium, away from that center of the field. So what's an atom? An atom is mostly empty space. Atoms are mostly empty space, from what they for what they know. So the proton's in the nucleus, is positively charged. Where's the electrons located? On the outside. So this does not really do this justice because the proximity of these two in this model, this electron would have to be a lot further away than what we show, size-wise, relative. So electrons on the outside, if you notice I put a negative with it, so electrons are negative. Now, by the way, which one do you think is more important in describing the characteristic of the atom? Do you think it's the proton, or do you think it's the electron?
What happens when you split in half?
Okay, so,
Is that possible?
yeah, I can't do it. Now, protons are indicated by this number. And that tells you how many are for that particular element. So if I say it has 21 protons in it, guess what characteristics it's going to have? Characteristics like scandium. If I said it has 8 protons in it, guess what characteristics? It's going to be like oxygen. It's going to have the same property as oxygen. Okay, so the protons are what really tell you what physical characteristics the atom has. Now, if we take a look at the chemical characteristics, it's probably the electron. The electron can move away from the atom. Protons can't. Protons are grounded. They have to stay at home. They don't get to go anywhere. Electrons, depending upon how many's out there, they can kind of go. Especially if there's something that wants those electrons really bad. This electron can be easily swayed to move out of the atom. Okay? Sometimes they can't be easily swayed because they might be too close to the nucleus to be taken away. And we know opposites attract. So if this distance decreases, what do you think happens to the attraction between them? Much bigger. If they get further away, less and less and less. So they're easier to take out if they're bigger. If they're smaller, they're harder to take out. Okay? Away from the atom. And then the neutron, good old neutron, it's kind of present to create what's called a nuclear force that holds all these like charges together. So can you imagine getting about, let alone 2 people, 10 people that just hate each other together and to stay together in a room or in like an elevator. Put 20 people that hate each other in an elevator. That's what's going to keep them there. The doors, right? They're not going to get out. Okay? But if you let them out, then there's a lot of energy because they're getting away from each other as fast as they can. So the neutrons are in the center, and they kind of have this way of keeping the protons together. Because we know like charges repel. Now, once you get up to 92, then you can't keep them together anymore. Once you get 92 protons, and then after that point, you cannot keep them. These are unstable after that point. So you get down into plutonium, radioactive. They don't stay together. Too many of them in there. 92 is the max. It seems they say what's called a critical mass, and then past 92 protons, it's too critical. I mean, they just fall apart. Okay, fall apart. Too much repelling between the protons in that situation. Okay, so kind of get an idea what the atom's mostly empty space. I wonder who that is. Who's needing to go? That's been the wrong number. Okay, so to finish things up, atomic number definitions over here. Okay, a number that indicates the number of protons in the nucleus. Okay, so it's a number okay. It indicates the number of protons. I'll use P positive for that, just because it's easy. It's a shorthand, so it indicates the number of protons in an atom. Okay, and we know it's in the nucleus. So if you want to put it in the nucleus, that's fine. In an atom, that's fine. Same thing. Okay, where's it located on your periodic table? Upper left. So it's in the upper left, and it's the bold one, and it's a whole number. So that's the atomic number, and it just indicates the number of protons in that particular atom. Okay? And it's found on the periodic table, yes. Mass number. Mass number indicates the number of protons and neutrons in the nucleus of an atom.
How do you get like hydrogen and stuff?
Hydrogen. You can get hydrogen from reacting metals with an acid, and it gives off hydrogen gas. That's one way you can do it.
So like, say you put like sodium in water.
Yep.
And you can just catch all the gas.
Any metal that's reactive with usually acid, sometimes if they're really reactive with water, you produce hydrogen gas.
Alkaline metals, those are...
Yep, alkaline metals, alkaline earth metals. Any metal, now there's some of them don't react with acids really well, and so you're not going to get any gas off of those. And we'll talk about that this year. We'll talk about reactivity table, and it might be at the end of this unit that we do some of that. Okay? So this tells you the number of protons and neutrons. Is this one located on the periodic table? And the answer is no. No, it's not. Okay? Because guess what? Isotopes are atoms of the same element with a different number of neutrons. Okay? That's what isotope represents, and we'll get to that last definition. And then atomic mass. Atomic mass, I'll go ahead and put it here. I think I can fit it here. Is the average mass of an atom. Okay. Is that located on the periodic table? They might call it, instead of atomic mass, they might call it atomic weight. So down here you have a key. And so atomic weight is, yes, it's on the periodic table. And it's the one that's a decimal form. So I believe on your periodic table it's the upper right. Is that correct? And it's the one that has a decimal number. So anything that has a decimal number, that is the average atomic weight. And we'll talk about average atomic weight. We're going to do a penny lab tomorrow. That kind of gives you a real-life example of that taking place. And then the last one on here that we'll have you fill out is an isotope. And then I'm going to give you an example to write down below what is an isotope. So an isotope isotopes, we could say, is an atom of the same element with a different number of neutrons. A lot of times the definition will say an atom of the same element with a different mass. Well, what's causing a different mass? Different number of neutrons. Protons have to stay the same. You cannot change protons. That's why I said they're grounded. They never get to leave. They never get to leave the atom. See, the electrons have got the freedom. They can leave. Some of them can leave, not all of them. So we have isotopes. So now I'm going to give you a list of 3 isotopes, and it's silicon 28, silicon 29, silicon 30. What do you think all of these atoms have in common or the same?
At least 28 or something.
Well, at least 28. Okay, but I mean, they're exactly, all of them have this exact numbers. Did you say, would you say? Oh, okay, I thought you did. What do you think they all have that's exactly the same?
Protons.
Protons. See, silicon, how many protons does silicon have? 14. Because the atomic number represents the number of protons in the nucleus. So this silicon, protons, if we listed them out, this one has 14, this one has 14, this one has 14. What's different in those 3? Different number of neutrons. So this 28 is called the mass number. What does the mass number indicate? Protons and neutrons added up.
So there's 1 proton of hydrogen.
Yeah. So, how many neutrons does this silicon have? This one. No. 28 is protons and neutrons. So, if it has 28 protons and neutrons and we know the protons, then we can determine the neutrons. So how many neutrons?
Subtract.
Yeah, so
15.
what would it be?
14, 15, 16.
Okay? So guess what? All of those in a sample that you hold in your hand of silicon, it's going to have all of those isotopes. Guess what? Okay, so the average atomic mass, this is the last thing I'm going to ask you. The average atomic mass for silicon is 28.085. Which one of those 3 do you think is the most common in my sample in my hand? Silicon 28, 29, or 30?
28.
29.
Why 28?
Because it's closest to 28.
Yeah.
Average.
Yeah. And it's probably got like 97% of your sample will have that silicon in it. Okay, so we'll talk about isotopes more in that. Make sure you have those written down. Okay? Did everybody get those punched?
Yeah.
Okay.